So this is gonna be a little geeky, it's gonna be a little fun. We're gonna have a little fun with this. I got some feedback last night about political correctness. I said, well, we're not gonna have any of that. So we're gonna get right into that, being unpolitically correct. Yes, I do have my Trump hair on, for those of you who are following the debates. So here we go. So this is all about networking and how you think about actually designing a particular network and what are the best practices are. You know, speed me up, slow me down if these are some of the things that you'd like to step on or hear more about, or we can do this offline in one of the rooms. But there's always challenges to going in and making a change, no matter what that happens to be. And this could be a life change, it could be a network change, it could be a technical change. You know, what training is involved, how costly is this? There's always going to be opinions and kind of trepidation about doing anything new. And so how do you get past that is literally through this information, knowledge, wisdom tree that we all go through every day. We acquire information from either other people or hands-on or reading things, and then we turn that into some best practices. And when all those best practices come together, you are super happy people. Yes, high-fiving yourself. Yes, look what we did together. As we saw in the first presentation today, they were very happy that things moved forward. But what people are really asking for, what customers are asking for is, hey, make the right-hand side work as well as the left-hand side. Why do I just want to have something that is not working as well or is not as predictable or I can't diagnose it if it doesn't work as well as the left-hand side? And that's what we're going to address literally today. We're going to get down to the weeds. You're going to learn some things. Your brain might burst with all the knowledge that you're going to get, but I think you're going to be happy with the material that is presented here because it's going to make you a network foo individual. You're going to have good network foo. So looking at it from a beer perspective is, you know, no two beer steins are alike. You buy a beer stein because of the capacity, the temperature retention, the grip and handling function, the cost performance ratio. I don't even know why there's a lid on this. I drink my beer so fast, I don't even need a lid. It kind of gets in the way. Does it make me look cool? Maybe that's the reason you're buying this new beer stein. Or maybe you just need to get Das Boot, and that's going to serve all your needs for that. And that also does look cool. Likewise, there's no two networks that look exactly alike. And this is because different customers have different requirements. In some cases, they want to do the amber and blue all together and create a purple. In some cases, they have remote productions or remote facilities where they need to do a spine leaf type environment. In other cases, like OB trucks or something that you could do more monolithic, or you have a single studio, is you can do a big switch. Now, obviously, if you look at all these, well, there's different challenges with each one of these, and we'll get to it, get through some of the details in this, and how to be successful in all three of these, by the way. So this is your roadmap to success. We're going to take you from 0 to hero in less than 30 minutes. So let's start off with what are the requirements. From an architectural perspective, there's certain things you need to start off with. And you start off with, what are the endpoints in mind? Okay, not just your endpoint. I want to think, there's manufacturers on the call here or on the webinar. Think about your product. Where does it fit? How many interfaces does it have? What are the characteristics of it? You know, what are the codecs that support, the frame rates, things like that. So think about all that type of stuff. Also think about, is there a beer requirement? Yes, there is, as you guys probably read in the first slide, there is a 2-drink minimum. So yes, there's always beer required. But more importantly, if you look at not just the endpoints and the hardware connectivity, you want to think about the flows, you want to think about the workflow. Is there any delay in the workflow you need to account for? And then also how you're going to do your routing. Are you going to do this through a broadcast controller or just IGMP and PIM, which we'll get into a little bit more so you can understand what that does. Does it need to be distributed or centralized? And then also, if you have a contribution feed coming in or you're giving a contribution feed, how do you secure that? Do you need to NAT that? How do you federate with something else? So this is what I call the Judge Judy effect. Every time I get into a project, I ask a bunch of questions and people go, why is the networking guy asking all these silly questions of me? Is he putting me on the spot? No, I just want to understand what's going on because I'm building the network based upon the requirements of the end nodes. It's not the other way around. You don't decide the network first and then figure out what you want to do with it. You figure out what you're trying to do first and then go the reverse. So going back to visualization here of your particular device, there's typically 4 different types of interfaces. There's a management interface that could be in-band, if you will. There could be an amber, there could be a blue for your resiliency of streams. And there's also could be an ILO connection. This is typically like on a server or something like that, so you can actually remote into it. And so how do you actually look at your device is very important to how you lay out your network. For example, you may want to have a separate management network, a separate ILO network, and secure those off between your transport streams. In some cases, you can't do that. For example, if you've got a transceiver package that has the management interface, amber, blue, and everything else on a single interface, well, that's going to be a trunk, and you have no choice but to make that a purple. Okay, if it's transport and management IP share on the same physical device, then maybe like a microphone, for example, then maybe that's another purple device, and you can only plug those in on, quote, purple switches. Another thing is single transport stream and management stream, maybe it's a microphone too, and maybe that's an 802.1q trunk, and maybe that also goes on purple, or you put your transport stream on purple and you put your management into this secured out of band. And then there's other different variations on this, and each one of these apply to different toolkits that you have. So starting off with the connectivity in mind, you need to figure out what that network looks like. How do you secure it? How do you keep your ambers with your ambers, your blues with your blues, and your IP addressing right, and things like that? What's interesting too is we've came across a couple of different products that have said, hey, by the way, do you have redundant management interfaces? And there are products coming out with literally that. Now, does that mean it's going to use a virtual IP address and connect to the management interface or the management network and virtualize that across the two links? Or if one goes down, one comes up? Possibly. In other cases, you have two management interfaces that you need to take a look at. But also, how does NMOS or Ember Plus, or I thought it's PLUS, not USE. So that's Ember Plus, I guess it's French. So where does this talk through? Is this through the management? Is this through your in-band? Or where does this connect to? So you got to consider all that type of stuff. As a network architect, what you're trying to do is reduce constraints in learning, constraints in bandwidth, constraints in deployment, constraints in knowledge, all that type of stuff. So let's talk about non-blocking versus blocking architectures. So clearly the guy on the left is a blocking architect. He does not know how to use the funnel. He's blocking there. He's a skinnier guy. Let's take a look at another pro here. Non-blocking architecture. You could tell this guy is a non-blocking architecture. In fact, I would even venture to say that he's a deep buffer non-blocking architecture. These are the jokes, guys. So it doesn't get any better than that. All right, so let's take a look back at that spine leaf.
We're laughing inside, Robert. It's okay.
Yeah, some jokes are just for me. So going back to this is looking at the spine leaf, and the spine, if you're not familiar with this, is typically an interchange, okay? So it's really just a connection between the other leaves. Or do you connect other devices to it, high bandwidth devices to it? This is one of those decisions you have to make. Do you want to be a purist and just have a spine for spine's sake and connect leaves to all the services, or do you connect things to the spine? In a monolithic case, what does that look like? How do you keep your ambers and blues? And what about the purples? Where do you connect all that stuff to? And what are the data rates associated with each one of these? So let's drill down to that a little bit more. Now, obviously, we're going to need some PTP in here, and I'll show you how to do this PTP only link in this slide deck here. So you want to keep PTP separate. It is the most valued transport that you have. You have to protect it and do it right. And here's how we do that from a PTP connection perspective. So what you don't want to do is leak routes from blue to amber or amber to blue. You don't want these PTP only links to carry the multicast streams or even control or monitoring, things like that. So there's a couple of ways we can do this. And your tricks is you can create an unused VLAN of 999.666 or something like that, and then stretch that across, but don't put an IP address on it. So literally it's just a VLAN that's common on both sides. And you can have separate VLANs on the top link versus the bottom link. So you might have 999 up here and 666 down here, and that works perfect. There's no actual traffic other than PTP going across it. The other trick is make it a routed interface, but don't put an IP address on it. Again, you can talk back and forth, but this doesn't mean you need an ACL. There's no real hard structure to this. This isn't difficult. You just go into the configuration on the interface and say no switch port, and that's it on both sides, and allows PTP to work together and not mix your amber and your blue together. So a couple of neat tricks there that are very easy to do to get PTP only. In the first presentation, they were talking about PTP feeders to all the different leads. Well, if you did this right and did like one of these tricks, you wouldn't need to do those PTP feeders, okay? So let's beat up. Let's take a look at one of the examples here. I'm gonna pick on Lee's product and John's product here a little bit. Just have a little fun because we've all seen these in the labs and especially in the interops. You got the Imagine SMP. We all know it has two 100 gig ports. Well, if we try to force this into a spine leaf architecture, these are 100 gig ports going up on the blue versus green. You can tell the date on this is because we went from blue green to red blue and then amber blue. So anyway, so it's two separate links, but you can think of that as a 100 gig link going up to your leaf. Well, for every 100 gig link I go to a leaf, I'm going to need another 100 gig leaf to go to a spine. In fact, I'd venture to say if I had 4 links up 100 gig, I would need 5 or more links between the leaves and the spine. Well, That gets very costly. Why am I doing that to myself? Why am I oversubscribing? Why do I have this non-blocking fabric to begin with? Well, this is not a best practice. What you want to consider is back to that constraint-based networking is removing the constraints. So what you don't want to do is overflow your bandwidth. Okay, that's the whole point of this. You want to have everything being active and use what you have, okay? Not worry about the constraints. So the idea is to take that spine leaf, and you can think about that spine leaf actually being internal to the switch. The switch has multiple network processors or ASICs on it, and internal to it is a fabric. There's two types of fabric. There's one that is more crossbar oriented, where flows can get pinned. And there's another type which turns the flows into, each individual flow into multiple cells. It breaks it up and it uses the entire fabric. We have a product line that does this, does actually both the left hand and the right hand side. So what you want to do as an architect is figure out what the flows are, and can you do line rate flows of 100 gig and multiple 100 gigs using one architecture or the other. Chances are the left-hand architecture is the one you're going to want to pick because that's the most efficient. And again, you're doing spine leaf, but you're doing spine leaf internal to the switch itself. So just in terms of scalability and numbers, so just handy facts, I attribute this to John. He loves to have the little handy facts on the slides here. So if we take the 48 by 100 gig, well, that's a 1500 by 1500 at 3G. Well, that's a pretty good size. And then the 144 by 100 is really a 4600 or 4600 by 4600. That's fairly big. That's bigger than any SDI router I've ever seen. So you can get fairly large with this just by looking at the right capacity and think about what your needs are. And again, this is a non-blocking architecture using like a 7504 32-port switch. There's also some other things you can do if you need 10 gig or 25 gig and use breakout cassettes. And we can go into more detail on that if you want to in the breakout room. But what we want you to do is think about capacity first. Think about the node connectivity first. Think about the constraints, because you don't want to overflow. So we're going to switch gears here and say, well, we talked about multicast, and you said that that was important to know and understand. So let's do this. So let's multicast at a glance. On the left-hand side, we'll say we have a thirsty patron, and for those people who speak German, ein Bier bitte. And on the right-hand side, and I've got to make sure I say this right, the bartender in the multicast says ein Bier schicken, which means basically I'm going to keep sending something that's sending. So I'm going to send a beer or receive a beer. So on the left-hand side, we've got our thirsty patron that says, bartender, please send me a beer. And boom, he gets his beer. So that's known as a unicast or a client request. On the right-hand side, the guy missed his connection. The packets are going by, but he's missing his joins. So the packets keep going from the bartender, and until you want it or can actually get to it is when you actually get that particular packet. Again, these are the jokes. Hopefully you're getting them. Hopefully it makes sense. So 3 types of traffic, and this is a refresher for many. Maybe it's new for some. Broadcast, which is one to everybody on the VLAN. That's a broadcast. A unicast is one-to-one, where it's initiated by a client, and connection is where the service is. This might be like a file server, storage server, things like that. Multicast is a one-to wherever you want to do the join. And this is where it comes in, is you could have a transmitter that doesn't have any receivers until it's needed. You could have like multiple cameras or whatever up, and when it's needed, then you choose that. So you have to look at these flows in different ways, okay? So let's drill down into that a little bit more. And this is where it gets a little geeky, so caution, but this should break it down enough so you understand what really multicast is on the switch and in the network. So absent a querier and querier IP address, both of those, what you get is flooding. Every multicast becomes a flood. And we'll see these in a lot of times where somebody says, hey, by the way, I just added my 4th IRD, and every time I add the 4th, I have traffic on here, and everybody basically goes down. Because that broadcast, that multicast is becoming a broadcast. Again, a multicast is a broadcast without a querier enabled and querier IP address on the switch. Now, what's also interesting is when you cascade these switches, we see this a lot with the Dante Ravenna's A67s in the world, is you have 2 switches cascaded together. Well, the left switch must tell the right switch, hey, I've got all these flows and I need to flood all these flows, literally take all those multicast traffic, whether there's a receiver or not, and send that across that link. Well, now you're using bandwidth that you never really needed to use. So how can you fix this? Oh, by the way, there's a tiebreaker in the querier, which is the lowest IP address wins. So the guy on the right wins because he has the lowest IP address. Well, there's a simple trick to this, which you put basically your querier address as zeros. And so what is happening is in this particular case, the microphones tell the switch, hey, I've got these multicast feeds. And then it proxy queries that information, not the whole flow, but just the update of the information over to where the query is. So he knows that the multicast is on the other switch. A very quick point in here is you have to look at all zeros. If this switch on the right-hand side goes down, you don't have a querier. This 000 cannot be a querier. So this works in some cases, but you want to make sure you have a very resilient network before you venture into this. But the best approach is to do layer 3. If you can do routing on it, great. We still have some Dante and some other things that say, I need to have this one broadcast domain for everything to work. Great. So we'll show you how to fix that, which is going back over here. But the best way to do it is layer 3 routing. Now, some people say, I want to route on every port. I don't think that operationally is efficient, because a lot of times you want to move from one port to another port to another port just to check things out or to deploy things very quickly. Maybe enable, like in GTNM TR1001, DHCP. So when you plug in, you get your DHCP. And what we were just talking about NMOS, use all the NMOS tools that are available to you. Just note that your TTL needs to be greater than 1, because there is a tax as you cross that layer 3 boundary. So TTL goes to 0. So that means if you've got a TTL equals 1, you will not cross that router boundary. Now, people say, well, this is routing and this is hard. You guys are all routing right now. You're on your home network, or maybe you're in a hotspot or something like that. You've got an IP address on your phone or laptop or whatever device you have, and you've got an IP address in the gateway. You guys get this. So routing occurs and you know how to use this. You just need to know how to configure it. And that's where the knowledge and wisdom comes into play. Is I'll show you a couple examples on how to configure it. And then once you have that, you're done. So let's dig into each one of the different multicast types. And this is critical for you to know so you can diagnose things. And it's very important in diagnosing things to know if it's an IGMP v2, which is called an any source multicast, or a v3, which is a source specific multicast. So let's pick on this star comma G any source multicast for a second. Now with multicast with a star comma G, because I don't know the source, I have to have this intermediary person that does an introduction. In fact, multicast flows are sent in unicast to the rendezvous point, because I know what that IP address is, and then the rendezvous point figures out what the source is. In some cases, if you don't do things right, where you have the same multicast address, you have this join that comes up to the RP. The RP goes, hey, you want that multicast address from here? Wait a second, there's 2 entries in here, 141 and 142. What is happening is you get both of these flows. So when you do a join with a star comma G, and you've deployed it so you have overlapping multicast addresses, you actually get 2 feeds that could overrun the link. It's definitely not what you want to do. So you want to consider your multicast in your amber and blue as completely separate multicast address spaces. So something to consider from the deployment. Now let's see how this works with, okay, well, you could say, well, yeah, so we're going to do S comma G everywhere, Robert. Great, thank you. But, and we're not going to have any star comma G. That's not true. PTP is star comma G. This is where things get really fun. So let's say we have our PTP grandmaster. We got a domain 42 connected up to a switch, which is not a boundary clock switch. And we'll do some just some sync follow-up messages. Sync follow-up get deployed over to the camera on the left, and also forwarded over to the microphone on the right. Because why? Because they've done a join. So Ethernet 5 and 26 have done the join, and it gets that. Now, what also happens is delay request, delay response. Delay request is sent from the PTP grandmaster, while delay request goes down to the camera, but it also goes down to the same delay request goes down to the microphone. And the delay response is responded to by each device. What's interesting about this, and most people don't realize, is because you joined, all these devices joined 224.0.1.29 with an anycast, or an any source, I should say, the camera receives the delay response from the mic receives the delay response from the camera. Yes, that's true, because it's sending to the multicast address. These devices are responding to delay response are sending packets to everybody. So if you think about a scalability issue, well, if you've got somewhere in the neighborhood of 40 slaves off of one switch, or end nodes, media nodes, what is happening is you have this flood effect of multicast. So this is where boundary clock really comes into play. But people say, well, I just need to have everything go to the grandmaster. Great, just know that you're going to be overrunning some multicast to some of these low-end devices, which may not be able to tolerate these heavy flows or a heavy number of flows. Then you can say, well, I'll put transparent clock in here. Forget the boundary clock. I want to put transparent clock because I want to have the update on the delay request, delay response. I want to update the time. Well, it doesn't fix the problem of all this multicast messaging going everywhere. So this is the issue with star comma G and with PTP and doing it in a certain way. So really, you really want to do boundary clock where you can to keep all those PTP messages from going to everybody else. Okay. Now you can say, well, wait a second, is this a scalability issue with my grandmasters, or is it a networking issue? Well, everything's a networking issue. So you're guilty until proven innocent, right? So in this particular case, we'll say, oh, we'll put two grandmasters on there, and I want to have 2 domains, maybe one for onboarding things and testing, and maybe another one for my production. Well, what ends up happening is, and you saw that in that first graphic, which is if you join 224.0.1.129, you're going to join both of these domains, both IP addresses. So again, you're going to have that flooding mechanism, and you're going to have it doubled because both of these grandmasters are going to join 224.0.1.29. So now you're exacerbating the issue even more. So you want to think about how you're deploying things, and maybe you want to take that domain 44 and put it off in a lab someplace for onboarding. So this thing I called S comma G, source comma G, I know the unicast address. I know the multicast address. I know I want to go to 0141 and 3141. Okay, great. I don't need a rendezvous point in this place. I don't need a man in the middle to connect things together. I literally go directly to it. I do the join and I get the video feed. This is very similar to like when you're doing a take on an SDI, you basically just plumb that together. So it's a very quick join. Now, if you want to join the other camera, you'll just do a leave and a join. This is what we call a break before make, and it just occurs. So the joins are easy to do, and this is natural to the endpoints because that's what they're intended to do. A broadcast controller on the other end doesn't respond to the joins. What it does is it does the joins for you. It plumbs the traffic for you. So in this particular case, this example is just all multicast related. But notice that you've got different unicast addresses for each one of these. This is why you can keep it all separate, and multicast addresses are unique as well. So you want to think about your IP address space as well for each one of the nodes. How many IP addresses do I need? How much multicast address space do I need? Now, by the way, in terms of multicast space, you have to be careful here. Very, very, very careful. We talk about this, and there's going to be a white paper working on about OB-VAN planning, multi-site planning, things like that. For every MAC address that's multicast, that's 01005E, that's multicast, you have 32 overlapping multicast addresses. Now, I've seen this a lot where people say, hey, for this particular site, I'm going to do 224.0.0.0, and then this site, I'm going to do 224.128, and then I'm going to keep my numbering scheme for my last 2 octets, you know, kind of the same. I go, okay, are you ever going to connect those sites together? No, I'll never connect them together. And then they want to connect them together, and they have to redo their multicast. So these are some things you have to think about up front, which is how do you do the allocation of these IP addresses to the particular end nodes based upon what they need. It could be that they have a switch internal, or they have 20 different multicast feeds or receivers on one particular interface, but you need to account for all that stuff up front. What's your address allocation? Now, the other thing to consider is NAT boundaries. So NAT boundaries could be on a contribution feed, ingress or egress. It could be because you're going from one facility to another facility. You need to translate your multicast and unicast address to whatever that site's requirement is. So in this particular case, we'll do natting, what we call twice natting. And actually, it's triple natting, if you will, because we're natting the multicast address too. This particular case will nat 192.168.0.141 to 66.141, and the multicast from 31.41 to 66.31.41. So that's 2 nats that are occurring, plus the MAC address. And we're going to go back to S, source-specific multicast, the S comma G. So we're going to join the natted address. Great. What happens is a switch nats that out, and it goes out, and it does a join this way, and then it keeps that connection alive. So joins in this particular case work really, really well in a NAT scenario. What breaks is, so for every pro, there's like a different con. What breaks is, and this is what we're talking about in some of the VSF community meetings, is, well, do we need to have some type of mediation in there that does the fixing of the SDP? Because remember, when we do this join over here with 2110, we have to get the SDP. Well, the SDP is going to represent the original value. NAT is just going to be a transport thing. It's not going to change what's happening in an SDP. So this is one of the things you need to consider is what does that camera's SDP do to the receiving node? What does the end node do? Does he even care about that particular IP address? Maybe he just cares about the characteristics of the flow itself. So these are things we're talking about from a standards perspective that we need to really think through. So the foundational requirements
Robert?
are, and I kind of these.
We got about 3 minutes left. Or
That's fine. That's what I got. Okay. So Start with the physical requirements. Consider your secure segmentation, route where possible, P2P boundary clock scale. You got to think about that, multicast scale, and and also consider your troubleshooting. The switch is looking at packets. The switch can be used for troubleshooting. It can be used for analysis. So don't forget you have that. And then put your toolkits on there. Whether you're from Bridge Technology, Fabrics, you got your Prism from the Tektronix, Telestream guys, use tools and use them effectively to help you resolve issues. So again, what am I trying to say is choose your beer stein wisely. Choose the network topology, choose the end nodes, understand what the end node requirements are from a physical and logical and flow perspective, and also from a security perspective, where you need to do those things. Do you need a jump server to get into that management network? How are you going to secure that? And then always think about the holistic aspect of this and choosing your stein. And if you do that and you do it all well, you're going to be a hero and you'll make people happy. So with that, that's my time. It probably went by very slow for you, went by very fast for me. If you have any questions, I'll be in the breakout room.
All right, Robert, thank you very much. And I very much appreciate you working the Oktoberfest beer theme into your presentation. I think that worked out really, really well.